Okay. Hi in the deep space and from the deep space to the virtual audience. My name is Martina Mara. I'm professor of Robopsychology at Johannes Kepler University Linz. And I welcome you on behalf of the entire project team of CoBot Studio. CoBot Studio is a project that I really like and that we have been working on for more than 2 years. It's an interdisciplinary project in which we explore how humans and industrial robots can communicate at the workplace and how we can improve mutual understanding between mobile machines and workers in industrial environments. So we are researching how different communication signals of industrial robots are understood by different human target groups. And to work on such questions, it's really needed that we have different perspectives and different partners in such a project. And therefore, CoBot Studio is really also a best practice, I would say, for how modern interdisciplinary research and development could work. So we have a consortium of 7 partners. The Robopsychology Lab, but also the Ars Electronica Futurelab and Johanneum Robotics, and the Austrian Research Institute for Artificial Intelligence, OFAI, and Polycular, who a game design and virtual reality studio, and the Center for HCI at the University of Salzburg, and Blue Danube Robotics. And, you know, to organize and bring together and combine all these different partners and perspectives, it's really needed that there's a great project management, and at this point I really want to thank Katrin Meyer from the Robopsychology team, who has been doing a great job since the start of this project. Today we're going to present some status quo results of this project and also show a live demo, which hopefully is quite interesting and fascinating for you. It's a kind of mixed reality demo. But to give you a short introduction about what we are up to in this project. So our plan is, or was, because we're in the middle of this and we already have some results, that we wanted to develop virtual reality and later mixed reality simulation games in which we can explore how communication processes in human-robot teams at different work or in different work environments could be improved. So we evaluate different kinds of CoBot. CoBot is short for collaborative robot intention signals. This can be light signals, but also non-verbal signals such as pointing gestures, for example, with regard to how well they are understood by the human team players and how the understandability of a robot affects user experience and, for example, also collaborative task success of a human-robot team. And based on our results from this project, we aim at deriving practice-oriented guidelines for a future user-friendly design of collaborative robot systems and their communication signals. And also, I think it's quite new and innovative that we use game, VR and MR game environments to study these questions. So one of our goals is also to evaluate the advantages and disadvantages of using immersive games compared to what we, at least as psychologists, usually do, classical lab studies or field studies. So we started to run evaluations in our game environment last year with a VR game, CoBot Game 1, and from the outside it looks like this. So this is also Katrin from our team wearing the HTC Vive. And Yeah, as said, our players, our test persons at the same time, they evaluate how understandable a robot in this scenario in virtual reality is when collaborating in different kinds of tasks. And we also look into how these affects trust, for example. So if a robot that is better understandable for humans also increases trust or is perceived as more trustable, and if users would accept such robots more, so based on how well understandable they are. And this is kind of an internal perspective, a user view. This is a very short excerpt of our first CoBot Studio game and research environment. And in this mini game, our players had to estimate as quickly as possible the target location of this robotic team partner in the room. And we manipulate certain factors in these games, like, for example, one player gets light signals of the robot and the other gets non-verbal signals and the other gets no signals. So based on different signals, we evaluate how understandable the robot was and how well they could predict, in this case, where the target location of the robot was. And we also implemented in situ surveys, as you can see. So I think this is also a quite new and important factor. Instead of retrospective surveys after this whole experience, as it's usually done in psychological research, I'd say, we have this in situ, on location surveys directly in virtual reality that are triggered by certain events in the game and that pop up whenever it's really relevant. Okay, so I think this is the point to hand over to Brigitte Krenn from the Austrian Research Institute for Artificial Intelligence.
Hello, everybody. We at the Austrian Research Institute for Artificial Intelligence are interested in this project, how a robot, which signals, which non-verbal signals of a human, a robot should be able to understand, and also which signals a robot should send to the human in order to be understood. Here you see on this side a picture from last year's Ars Electronica, where we had these interactions, or we had the real robot interacting with a human. And when you look at the picture, you see almost everybody in the room is looking more or less at the robot and this, the human. The robot and the human look at each other, so they have attention to each other. When you look at the other picture on the right side, you see the robot looking at Martina, but Martina is not looking at the robot. Martina is looking somewhere else. So, and when you see how close the robot is in the back of Martina, this brings us to the next topic. No, not this one. Oops. The proximities. It's very important how near or close we are to each other, either artificial agent or other human, and this depends on what do we do, what is the situation. When a robot is in my back and I don't know it and then I realize it, I really get startled. When me and a robot are working together on an object, we might lean over the object and the robot is super near to me, and this is okay. And now we come to the next aspect, which is movement. When I point somewhere and you, for instance, see me pointing, your attention is also at that object or wherever I point at, and I see you, that you are looking at, so I know, okay, we have established attention. And this interconnectivity between sending signals and interpreting signals, that's what's the important thing, and that's what we're looking at.
Thank you. So, hello again from my side. I'm Bernhard Reiterer from Johanneum Research Robotics, and I want to briefly talk about some important aspects that we gained from adding our Chimera robot to the CoBot Studio project. So our Chimera is a very useful robot. It can do a lot of cool things, but for making the step into VR, it had to gain a few new abilities, such as doing gestures, reacting to gestures from the human, interacting with virtual objects, pointing at objects or at the user. So in sum, we had a quite large number of building blocks from which we built complex behaviors, which allowed the robot to perform what it is supposed to do together with a human. And this is more complex than what the robot is usually meant to do in industrial contexts that we usually use it in. So it was really useful to have the freedom of VR that CoBot Studio gave us. So we were a bit lifted from this box that safety constraints usually impose on us when we decide what a robot should do, because of course you cannot let a robot work closely to a human with the danger of the human getting hurt. So safety is an important factor for us in almost everything that we do. And the CoBot Studio team is currently in the process of porting the latest game to the deep space here, where we then can use it together with the real robot, with the real physical Chimera. And we will still be able to perform the same scenarios here. And this is possible thanks to a common interface between the game and the robot. So this is an interface that does not care whether it talks to the real robot or to a simulated one. But of course, we will have to step back a bit from these safety relaxations that we did in the first place and reintroduce some safety constraints so that nobody gets hurt. Another important thing for us that we learned in this project is how we look at robot movements. So if you look at these bottom two images here, that will start moving in a second. Yes, these are two robot movements that make the robot do the same task. So the robot should go for an object that it is going to pick up. And this is from a sequence of our first game where the user had the task to guess which object it is that the robot will pick up. And we saw that you can actually disassemble this movement into different parts. Some of these parts can be seen as cues for the human which the target object is. So for example, at some point the whole arm is rotated towards the object, or at some point the hand, so the robot gripper is rotated or is opening to fit around the target object. And then of course also the robot has to move forward, and at some point it has to move down. So once we disassembled these movements, these movement parts, we could reassemble them in different ways to see which part, which cue is most effective in giving the user a hint where the robot is going to grip. So we are waiting for results. These are currently under analysis in a master thesis at JKU. So stay tuned for more from CoBot Studio on this point. Now I can pass over to Michael.
Hi, I'm Michael. I'm from Polycular. We are a game development studio. Our main task in this project is the development of the VR environment and the software architecture. So some of the biggest challenges in this project were to get the network communication running between all the devices that we have, so the robot, the VR environment, this environment here, the deep space. Also, we want in the project quite natural interaction with the environment, so you can basically do everything with your hands in free movement in virtual reality. You will see it in a moment in the video. And of course, there were some requirements because these are experiments, so they needed to be deterministic, behave deterministic, and needed to be repeatable. Yeah. This is the VR setup that the person who carries out the experiment wears. So you basically have a wireless headset. You can run around freely in the environment. The headset is a Vive Pro, which also enables us to do eye tracking, so we always know where the user is looking at. There is a device mounted in front of the headset, this little black thing. It's called a Leap Motion controller, which basically enables you to track your hand movement. And as said, yes, it's wireless, so you can walk around freely without any cables in the VR environment. This is a video. It shows a virtual representation of the human body. So we are able to track and animate the whole person who is the Proband. And visualize this person in virtual reality. And now we have also a virtual camera setup, so we can film the whole experiment from several different angles. And yeah, this is a short video showing this. So here you can see also the hands, and it also supports hand gesture detection. So you can basically control the whole environment with gestures like thumbs up or stop signal. You can show the robot stop and then the robot stops. Yeah, this is where I hand over to Roland.
Okay, thank you very much. My name is Roland Haring from the Ars Electronica Futurelab, and what you have seen so far is that we did different setups, how we experimented with these robots. So some of them were real robot in real space. What Michael just showed now is a virtual environment with a virtual robot where you're completely immersed in VR. And what we are looking at is how to combine those things and how to put a real robot and a real human being together into a virtual space. To basically try to combine the advantages of these approaches. So to have really this physical presence of a real robot, but still also the flexibility of a virtual space where you can really do whatever you want, basically. And we want to do this here in deep space, so this is basically the current work in progress that we're doing, and there are a lot of challenges that arise from that. So one thing is for sure, that the perspective must be totally correct that you have in this space, because the physical robot aligns with the projected virtual space, so this is like a stereoscopic projection, but in order to really overlap correctly, you need to measure exactly the position of the human being in this space. And also, all of these gestures that had been explained also need to be measured, and you need to have additional sensors which allow you to do this. And this was basically one of these main also research tasks, to extend this space here to also be able to do something like that. We're doing this like with different approaches of optical and inertial tracking systems. And in the end, we come up with something like this. So several additional sensors set up here in the deep space, measuring all kinds of interaction, and we also, or can use this also for this virtual production, basically where the camera is basically then the field of view for the perspective. So this is a similar principle, but in this case applied to this human that's interacting with the robot in this space. And to make this a bit easier, how to say, easier understandable, we would like to make a short demonstration of some of these basically building blocks that we are working with. So I must say that this experiment here in deep space is work in progress. It's not finished. So this is basically a live demonstration of something that could fail at any point. But let's try it, I would say. So Anna is wearing now these glasses which have these antennas which are used for the tracking system, and what you can see is that when she's moving around, the whole perspective of the space starts to move as well. And this is happening because it's instantly being calculated exactly for her field of view, so that she has a correct perspective. And this would now allow to put also a physical robot in here, and the perspective of the physical space would correspond to the virtual space. This is very important, so otherwise you would not understand what the robot is referring to, for example, if the robot is pointing somewhere, because then the perspective alignment is very important. So you see, it has actually quite a huge impact on the projection when you move around in the space. And what we can do now also is to hand over the glasses to the camera, for example, so that the viewers in the live stream can see basically now a correct perspective of the experiment. Let's do it like that. But this opens up also more possibilities, because now the system knows where, for example, this camera is. And this allows now also for, in this case, a simulated robot. So we can also have the virtual robot here for sure. Later for the experiments we will have the real robot here. But the robot can also now react to the position of the camera or point towards it. So let's see if he's doing it. Yeah, well, yeah, not exactly, but this is exactly, and okay, now it's working. So this virtual robot can refer now to any physical position in this space, and this allows now basically much more interactive scenarios that can be built. But we can also use this for communication. So Anna also has this glove here, and this glove is tracked as well, and when she raises the hand, then this can be interpreted by the robot as a gesture that she needs the attention of the robot. And now you can develop something like a non-verbal communication between a virtual robot and the real people in this space. And now the robot is moving to Anna, as he understands that this is what she tells him to do. And what we see here is now more or less this traditional operation mode, I would say. The human controls the robot and the robot follows the command. But this can also be done the other way around. So especially for CoBot, it's very important to collaborate. So that means that also the robot has intention, also the robot communicates with the human, and together they need to do tasks. And this is then also something that we perhaps can see, that also the robot is moving to another position, but also probably, let's see, communicating to Anna. So I mean, what we see here, this perspective distortion, this comes exactly from the fact that now for the people in the live stream, it looks correct. So this is intended. But now when the robot does a gesture, then also Anna can go to the robot, and the robot would know where Anna is in the physical space and can also react to this. So these are now basically just very basic things. But this is something like the building blocks on which we can build more complex scenarios and experiments where we really have certain tasks for people that they do not know in the beginning what exactly needs to be done, but you need to communicate with the robot to find out, and then jointly solve tasks which are hidden basically inside of this virtual world. But I would like to hand over to Martina at this point again.
Okay, thanks Roland and Anna. And in the end I would like to tell you that we're gonna run experiments within this mixed reality game and research environment in January 22 here at the Deep Space. And then, as Roland said, we're gonna put a real human, and this could be one of you, and this real robot, Chimera, here in the Deep Space in this shared virtual collaborative environment. And if you ask yourself, why are there fish swimming around in the back? This is just because the game environment of this new study is an underwater research platform from which you, in cooperation with your robot partner, have to collect plastic garbage from the ocean. So this is the task, the collaborative task of the game, so to say. But still within this setting and this environment, our questions are about how well understandable is the robot to you and how well you can succeed in the collaborative tasks. So if you are based in Linz, or if you are up to coming back to Linz in January 22, please just drop us a line at info@CoBotStudio.at, and we're going to invite you to participate in this study in January. Thank you very much.